И снова всем привет.
Hi everyone again. So I hope you had enough time to take a rest. In parallel, we are running the ATT&CK contest. You can find the address at our website. It's a very interesting track. Would you please join in? It has very interesting prizes, and we'll continue with Nikolai from InfoTex. He's going to speak about how he be using his encoder techniques to analyze anomalies in network traffic using TCN. I'm Nikolai from InfoTex. I'm going to be talking about the detection of the attacks in network traffic with the use of the codings, advanced persistent threats, pose a lot of threats because they are arranged with an organized group of individuals to make an attack from a targeted organization. Conmen are using a wide set of tools for their attacks, and they are structured. Such attacks are clustered into different stages, and some of the stages should be performed consecutively because they cannot upload data without being granted privileges. APT attacks are persistent and long, so they may attack for a long time, get access to new data, upload the data. For classification of the stages of the APT attacks, different methods are used. One of them based upon MITRE attack matrix. It splits the attack into different tactics, 14 of them. Each of them can have different techniques. In reality, not all of the 14 tactics can be utilized. Some of them can be skipped. Initially, they may get access to database in order to look for more vulnerable data. Another method which can be used here would be the life cycle shown here from Mandiant attack. Some of the stages look very similar or look very identical to the MITRE because they would need to get access, hackers need to get access, they get privileges, but hackers will not always go through all of these stages consecutively. Sometimes they would just need to go back to find the data they needed. We mainly focused on identifying tactics, for example, server negotiation, etc., and we used different methods for detecting such attacks. Let's talk about them. These methods are split into two. Violations detections like signatures, empiric rules, expert systems, and anomalies detection, statistical methods and machine learning methods. The key difference between these two approaches is the information upon which these methods are based. The violations detections are based upon the information about vulnerabilities or exploits, and we get very high precision because if this signature is targeted at searching for these violations will be detected. Such methods are very productive because these systems do not use or utilize any complicated mathematical models for cross-validations, but they also have quite a number of disadvantages, like avoiding the threats detections. For example, if the hacker knows what these systems react to, they can bypass them or use some legitimate tools, like, for example, Windows MITRE instrumentation. And naturally, so far, information does not exist about these violations or signatures. Such threats can overflow the detection methods for anomalies. They are based upon the normal behavior of the system, and they do not use the violations information at all. So such methods may become universal. So these systems will always consider violation any deviation from the normal state. And different methods may have different specifics, and such methods, in theory, need to identify the attacks of the 0 day. They do not use the information about the violations. By using such methods, we can bypass the detection of violations. If we build a normal system behavior, the hacker may actually suspect the behavior of the system, but in the neural networks, even the developers cannot say with high level of precision what would be the dependencies, patterns considered as normal and which one considered as abnormal. One of the disadvantages of such models would be their never urgent need for frequent updates, and sometimes they can be updated on a weekly basis, and they do not use information about violations, and they do not have to be updated very frequently. Yet they have to be trained, because any normal behavior of the system changes, like new hosts are added or some time elapses. So these changes are required. They can analyze comprehensive attacks. If we're talking about network traffic, these signatures can take into account each session, each packet, regardless of one another, without using additional information about the time distribution of network traffic. But these methods have some disadvantages as well. First of all, they are very demanding for resources, so this model is normally very complicated, so complicated neural networks are required, so validation, cross-validation are required. And with the use of such methods, the precision of the qualification of the attack also suffers. We cannot identify exactly which would be the tactic. And to understand what would be the root cause of the anomaly sometimes is difficult, and it requires additional investigation. Yet, if we study the APT attack cycle, we decided to use these models of detecting the attacks. They use legitimate tools for detection, like interacting with the server, interacting with some legitimate site. Based upon network traffic, we will be detecting such attacks. Here we have used the transport level sessions and the information about them, like the host identifiers, the numbers of ports, the numbers of bytes per packet, aggregations, the numbers of bytes per second. We also used the flag information in the sessions which were sent in the course of one single session. By using anomalies detection information, we can take into account the sessions in time, and it will look approximately like this. We have the transport level session. Each section is a vector. Our model will be taking a look at a segment and make a decision whether it's a normal segment or not. Then this window will shift session by session, and the upcoming segment will be analyzed in terms of its validity. I should say that normally this window is quite wide, and the shift of the window is much smaller than the window itself, so that we can segment it in a better way. Now we can talk about the tools. What would be the tools that could help us implement this model? We used convolutional neural networks. What's neural networks? They look like this. We have a few layers, corresponding layers, and each element of the layer is built upon the elements of the preliminary layer. And we may study interaction between all of them. Convolutional neural networks are using the mechanism of the core, which is projected at the entry input data and is helping us research dependencies, space dependencies. If we run a parallel with the previous slide, the input data would be just what we saw at the previous slide. So that's what we need to bear in mind dealing with these schemes. When we work with the convolutional coordinates, what kind of advantages we use using convolutional neural networks? First of all, it's the ability to find local and global spatial dependencies. That's exactly what we need, because we would like to find the dependencies in the time row, and we also save the resources. With a single core, we don't need to build multiple connections, because we use the single core effect. So we can work with the multi-measured data, and we can input it into a mathematical model. Let's talk about the architecture we used. We used the so-called TCNs, temporal convolutional networks. Each next and following layer equals the number of elements of the previous layer. It uses the temporal convolutional method. Only those elements are included that existed previously. Also, we have the dilation here in the convolution. Not the neighboring elements interact, but with some spaces. And we use an X1 convolution to regulate the number of channels of our data, to move from one layer to another. If we use these models, what are the advantages that we get in here? Well, we can work better with the flow of data. To get the result, we don't need to have the result for the next point in time. And we can also measure time dependencies by using these networks, which we need sometimes. The advantages can also be running the recurrent neural networks. Recurrent neural networks cannot give the result for the concurrent neural network before the previous result is obtained. Yet this model does not have such a deficiency, and it can move from one layer to another, and thus helps us run these in different tensor and parallel cores and improve our efficiency. We can use the wide window here in comparison with the recurrent neural networks, which can be trained in the worse fashion. They also have some problems with the attenuation, which prevails there. And here you can see it in comparison. The time and recurrent neural networks, which I've taken from an article, it shows some errors with different time points with the entry data. With the use of the 1,000 time spots, recurrent neural networks are in the higher level than temporal neural networks. Now we would like to talk about how we are going to build a model of normal system behavior. The autoencoder architecture will help us with that. This model should give the same object in the output as the one they had in the input. The amount of information about these objects should reduce. Thus, if we train this model with a normal set of data, it will be able to identify the patterns and help us rebuild it. The mistake here is a metric which compares the input and the resulting object. We have the segments. We will have the mistake of the reconstruction, which will be much higher because the patterns will be different. Approximately like that, the ultimate architecture of the network will look like. A simple network is shown here on the slide. In the decoder and encoder, we have just one layer. This is the convolution applied, then pooling occurs, then another convolution occurs, and we restore the size and form of data with the upsampling, and we use yet another convolutional layer. Thus, these networks will help us build the behavior of rows to identify the anomalies there. Then we conducted a number of tests to check the networks, identify whether it's capable of identifying anomalies, and we carried out a number of synthetic tests. We took the data from the emulated network, where we carried out an APT attack. Then we moved to the real network traffic with the embedded APT attack. In order to move to the tests, we just need to understand what would be the anomalies there. Spatial, time, and combined anomalies. Let's come up with a few examples. So let's just imagine an abstract system made up of 30 points which show the position of the system at a certain point in time. As time elapses, a sine wave will protrude, and you will see the behavior of this system over a certain span of time. You can see the curve. You can see the waveform. We just need to describe this at a few points. Instead of a sine wave, at certain points we have random parameters that do not form a wave shape, and on the contrary, time anomalies occur at certain points in time. Here you can see that the x15 point had no anomalies, but it had some sine waves. Yet x equals 25, we inserted the anomaly, a time anomaly, in this space of time. And it does not show us beautiful sine waves, but it shows some ugly detections described as anomalies. This is a combined anomaly, and very often we face with such ones. Can our model detect anomalies of different time? Let's conduct synthetic tests to do that. 30 time rows with sine values. We added noise there just to understand the noise factor. And we took only the one, the second, and two in the third one to understand how this model would react. With some time delay, so that they do not overlap in time. Then we trained the model, and we carried out a test, and we ended up with this mistake, the mistake of the reconstruction, where we had such an anomaly. It's also an abnormal one. A conclusion can be made that all of the anomalies had been detected. But in this case, the abnormal behavior was, instead of those signs, we had random values. But normally, anomalies can be of a more complicated kind. There could be a dependency between two. To understand whether our model is capable of detecting them, we'd build 3 different patterns. And these patterns could have had a different scale. Ultimately, we used 2 time rows, and the normality of the work of a system was identified by the dependency of patterns. The combination of patterns were normal, all the other ones considered abnormal. So we came up with a test set built upon such patterns. We added noise and the 3 anomalies. In A, pattern equals 0, and pattern 2 in the next case. It's an anomaly. Here we can see the errors. Everywhere we detected anomaly, the reconstruction error was abnormal, and we can see at which points in time anomalies would occur. Thus, we proved the efficiency of our model with the synthetic data. Then we moved to the network traffic. One such example was Pico domain data set. It's a set of network magazines from which we only took the transport level sessions, and here we have the representation of data for 3 days, and the APT attack was carried on for those 3 days. Emulated, you can see also the horizontal moves of a hacker. We can see all of the stages of the mal-classified attack. For example, the hacker gets access to one of the hosts using the WinRAR vulnerability. Then they use the PowerShell, they established foothold, they escalated privileges with the use of the hot potato exploit. Then they started moving in a lateral direction using WMI, etc. This cycle would always mean the interaction with the command server. They collected all of the data of the users and they exfiltered the user data successfully. How was this APT attack marked? The attacker had some flaws. 2 minutes differences. At the same time, all of the sessions which were about interacting with the command server were not marked either. So the creators of that came up with a chart of the activity, bar chart, which portrays the activity of the users on day 2 and day 3. Abnormal activities with the iNet and iScreen websites are detected. Those were the sites used, and we understand at which points the interaction with the server occurred. And the first intrusion, all of the data for day 1, with the exception of the time in the evening where there were no attacks, etc. We learned on this data for day 1, and we built the reconstruction error chart. The first thing we detect here is that the reconstruction error in the normal behavior for the first day is higher than for day 2 and day 3. It occurred because if you pay close attention to the upper chart, you see that the activity of the users on day 1 was much higher, was varied, but on day 2 and 3 the user activities was less varied and was much lower. So it's not representative. Seems like the normal behavior on day 1 and abnormal on day 2 and day 3, and that's the reason for error. So in order to measure the boundaries of anomality, we just measure day 2 and day 3 separately. Now we can make a preliminary conclusion that interaction with the server was successfully detected by the model of the neural network of ours. Let's just take a deep look at the reconstruction error. The initial access was detected successfully, with some deviation, however, with these 2 false positives. Let's just take a look at the reconstruction errors on day 2 and day 3. We also used validation here, which was based upon normal traffic on day 2 and day 3. The picture is more or less exact. All of the detections are valid. All of the intrusions were detected. Let's focus our attention on the following fact. If we take a look at the first bar chart, we'll see just by the activity of the users, we can identify where the interaction with the server occurred. And the real network, such bar chart cannot be created because the server interaction will not be that prominent. So in order to complicate the task in this data model, we did not use the IP addresses at all. Yet the interaction with the command server was still detected. It's an interesting result we ended up with. Then we moved to the real traffic, and we used a normal set of data, the InfoTeX network, and in the emulated network an APT attack was carried out, and you can see the schematics of it here, which was much more easy than the previous one. Less stages, less network traffic inside it. It was carried out in the emulated network, and the sessions were embedded into the InfoTeX traffic, taking into account the topology of the network and a very realistic attack was integrated. Then we trained our model with the normal data set, and here we can see that the sessions belonging to the attack were few, and they were focused with just one area which took just a few minutes in time, and this attack was successfully detected by our model. And this is another chart in closer proximity showing the success. Then we revealed a few disadvantages of the model. First of all, it's very hard to detect sparse attacks. If there are more sparse attacks, such abnormal activities will be diluted with normal activities. If there were 10 sessions, 10 network sessions, but they were very, very sparse scattered around among 10,000 of normal ones, we wouldn't be able to detect it because it's diluted and is very sparse. Another deficiency of this method, it's an insufficient localization of the attack. We cannot say very precisely at which point of time it started and when it ended. And the last deficiency here is very hard to identify the stages of the attack, which is generally true for other models as well. How can we improve the model, and how did we actually improve it? By using the following method. Take a look here. We have a time frame from networking sessions, and we select this window. So we select a segment, we make a reconstruction error for it, and then we take a step so that it would be equal to the width of the window, and make a reconstruction error for each particular point. And if we dilute this attack with lots and lots of normal traffic, but we use this following scheme, we will have the following error. We will have a much more thick layer because we diluted abnormal sessions with quite a lot of normal network traffic. And here is the result. We can see that we are getting very low precision. We have quite a lot of false positives here. Yet, where we can see the APT attack, we see rough edges, and these rough edges indicate the network attack. Thus, we segment it, and we can identify when the attack started and when the attack ended. Making a summary, I should say that we were able to build a convolutional neural network successfully, which could very successfully identify APT attacks in the synthetic and real data sets of the network traffic. I'm done with the main part of my presentation, and I'm ready to take your questions. Please use your questions please use microphones for your questions. Those who would ask interesting questions will get T-shirts. Hello, I'm Nikita Kurganov from Yandex. I have a few questions to you. What's the precision and completeness? I didn't see that. Question number 2. We saw WMI, we saw auto-run, persistence, so it was Windows environment. But what if it's not Windows environment? What if it's a Linux? What if it's the kernel vulnerabilities? What if it's a Mac OS or Linux environment? Did you test your model on such platforms, apart from Windows environment? And question number 3, do you have a data set with APT attacks which is targeted for Linux and Mac OS? Thank you. You mentioned recall and precision. We are looking for the reconstruction error not for a particular space and time, but for the entire segment. And this model trains to localize and identify this particular error. So we cannot just simply take recall and precision. Other methods need to be invented. We can evaluate this work like this. As for different systems, we tested it with different sets of data. SAC ADS 2017-2018 emulated Linux as well. I don't remember exactly which particular methods we used there, but I remember precisely that Linux machines and Windows machines were used there as well. But we are not targeted at making particular tactics. We're trying to detect abnormal behavior of network. I think I answered all of your questions. Next question. I'm Grigory. You say that you tested it on your own network and you emulated this attack. Reverse shell, password to the server, data filtration. But then you just tested a small... you had a very small detection. Did you detect part of the attack in a very short space of time, or it was the complete attack? We just studied network traffic, so all those sessions which belonged there were few of them, so all of them belonged to that particular attack. So initially they were integrated in a very small space of time. So I think it answers your question. Yes, thank you. I'm Andrei from Sberbank. Two questions to you. So I think it would not be a good idea just to give this raw data before feeding it. How did you pre-process the data before feeding? And how can you measure these two models? You use different type of approach. It became better, it became worse with the proxy method. Did you use it? As far as the first question goes, IP addresses were just split into bytes and they were normalized. If the work of the network does not have a lot of devices, you can use the identifiers of the machines, but you just split the simple IP address into four features and you normalize them. As for the comparison, yes, of course there is a problem in comparing the models. We can compare these models using charts and graphs, but we are promising and working more on this last bar chart where we measure the reconstruction error, and then we'll be able to understand which particular metric should be used here to identify the quality of the model. But such a problem does indeed exist. As a recommendation, it was from our colleagues in the neural networks, you just add the embedding layer, so you get all of these essences through embedding and so forth. Thank you for your presentation. I'm Pavel Filonov. A few comments first and then a question. People asked about the Memento anomaly bench work. It comes up with the proxy metrics, which takes into account the delay between the detection. But can you just roll back to slide 29? The threshold identification, that's what I didn't get. With the normal behavior, the threshold is 0.45, and then on slide 30 it's 0.25. How come that change occurred? Good question, but I partially answered it. If you take a look at this upper chart, this is a normal behavior on day 1 and day 2. It may be different. So training on day 1 and then testing on day 2 is not a normal thing, because this normal behavior may be different. So the reconstruction error may be different. So we took day 1st and day 2nd and day 3rd differently, separately. I mean for day 2 and day 3. So in the live system, you could have understood that there was an attack just after drawing the line in the end of the day, right? No, when the system works, it has some normal behavior. Based upon that, we can track it, track this normal behavior. It's basically more a problem of a set of data. Thank you. And you compared it with the recurrence. It's an interesting comparison, but I think today, if we really wanted to compare different types of approach, it would be nice just to see what recommended well. Transformers, for example, NLP and transformers really show really well in this area. Interesting insight. Or you may alternatively take a very simple method, an alternative method in the window mode, and see the detections, because it can be applied here with a time coder, and in its essence, it's much simpler. It's just a comment in the end. So there may be a simpler example. I think I need to study this question much more. Thank you. Thank you. Hello, I'm Andrei Matskevich, and thank you for your presentation. Could you please explain more in detail the processing tract from the moment you get network packets to the input to the neural network? From speaker domain, we had the logs from where we only took the traffic, the information about the sessions of the transport layer, and we had some features there, IP addresses, the numbers of ports, and we only used some ports because they were randomly generated. We used the number of bytes, packages, and the aggregations. We used the information about flags, which were also coded. As far as normalization goes, we used the non-conventional methods there, because we take a look at the distribution of the longevity of sessions. You can see a big threshold and a big step, and then long plateau, because some parts of the traffic have very low duration, but normal traffic has longer duration. So the question was about normalization of that. We use different combined methods for that. Starting from classification, ending with the detection of the so-called threshold, because we do not work with the normal distribution, we work with a similar distribution. So we divided it by border, we digitized the data, the packets which were much bigger, so the comprehensive approach was used there. So it was a good question about normalization. An elementary unit, the value of parameters from one session, right? That's what you take into that. Now, the input data is the segment. We have the data from the segment of the time frame, That's the input data. And we make the decision about the normality or abnormality of the time frame. In the network traffic, you have a huge number of subscribers, and you have one session running after another. Do you combine them, or you take just as a window without actually dividing IP destination, port destination? We do not divide it. But after the reconstruction of the vector, how do you select the threshold to say that there was an anomaly? This threshold set upon the threshold of the error of the normal traffic, and just 1.5 measured by the quartile distance. That's how you select the threshold. Thank you. Thank you. I'm Ruslan Kulagin from Bauman University. The question about transformers, wouldn't that take too long and we spend too much on infrastructure? And when I was looking at this chart, it seems like what would be the real case? Weekends, I guess it's weekends. Did you take into account weekends when no one goes to the office and then all of a sudden problems start? Or maybe it's the night time. So I think the time frame should also be taken into account. And there may also be a question about the size of the batch. Why did you decide to go batching? And maybe you could have skipped a sparse attack, which you mentioned. They would be sending one request into a batch and act sparsely. Speaking in terms of the weekends and weekdays, but normally this window time, it's 5-10 minutes, but the sets of data like that are very rare, and we cannot actually check this model for such days that you mentioned. But in the production run, in the production phase rather, it makes sense to do, because abnormal behavior may be different on certain days. And what about the sparse attack? I was asking about the sparse attack. What was the size of the batch, and what about having the risk of using this mean average? In actual fact, this batch should be selected in the time frame for 5 minutes of the network traffic, for instance. So if this is a sparse attack, there would be a problem finding it. But I don't actually understand the point of your question. Of course, when we select the time frame, the window, the time window, if it's a sparse attack, we may have some problems, but if it's a dense attack, we don't have any problems at all. And another question from the floor, which we didn't hear. We can work on this traffic. You can detect this attack by it exceeding its threshold. Or you may alternatively use some network traffic filtration, if you like. Yes, please. I'm Nadezhda Kusakina. I would like to clarify. Did you take into account the payload and the amount of payload and package, or you skipped that? I think in this particular set there was no such thing, but there were sets of data when we had quite a lot of parameters, like up to 85, and we did have such parameters. So normally the real sets of data that we can utilize, they don't have the complete information about network traffic. We operate with the files which contain this information. Okay, understand. The second question about your model developing. Currently, your model indicates that there is a problem, and it indicates the time, space when the problem is detected. You have one sensor to identify this anomaly, but in the real infrastructure, you just need to have a few detection points to detect such anomalies. A few detection points. Well, we conducted. It's more about production. This question is more about production. We studied the use of such models, but I didn't quite understand this question of yours. Your model implies that there is an anomaly, but where exactly is it in the network? Well, there's a problem with the anomaly, and it is very general to all of the anomalies, but we can make a reconstruction for each of the parameters, and based upon that, we can make a conclusion of what anomaly is all about. Sometimes it's not quite right because we have quite long dependencies, but if we operate with synthetic data, for each of the parameters, you could track down where exactly and how the reconstruction worked. I think we just need to test it. Hello, thank you for your presentation. The question is, you considered this anomaly in the process of work. So in actual fact, we launched this model when the hacker is already sitting there. How can we detect the malicious part in the training phase? Well, such a problem does exist. We don't have a normal traffic, so we cannot build the model of normal work and normal performance of the network. But what we can do, well, we don't know that we have hackers in the network. But if we build the normal model, we will not detect it, but we will detect the next one. If it logs out, we will be able to put our finger on that moment when they log out. So it's one of the options, I'd say, yes. I really wanted to reply to the previous question. We are working on this detection of the threshold, and we can see some splashes. If the hacker was just doing something in the attack while we were gathering normal traffic, making a mobile model, we can see some splashes, and we identify this threshold not by splash, but with a normal traffic. Then this threshold will be lowered, and we'll be working with this poisoned traffic, and we'll be able to track this anomaly. Yes, basically this approach can work. It can work, and such anomalies in the network traffic, there'll be fewer. But we can assume that half of the traffic may be abnormal. So I think that was the question. But this is a very hypothetical scenario, I think. Thanks, everyone, for your questions. Thank you for your presentation. What was the questions that you liked the most? I think actually the very first question, I don't remember who it was from. It was a very, very comprehensive one. Which one would you choose? Let's take the white one. And another complex question from that man in gray. From the third row. That's where you should have used the white one. And your question was quite interesting about the specific features in the set of data. Yes, thank you very much. Thank you. There will be a 1 hour break for here back at 3 p.m. We will have reports about the big data safety and security, GANs and biometric security. So please join us back here at 3 p.m.